Good afternoon, and welcome to Lecture 10 of Mathematics 208, Quantitative Models for Businesses. Let's get started. It's a bright sunny day, so obviously I've got a whole bunch of glare going on behind me, so I'm actually going to turn off my camera pretty fast here. So I'm going to do that right away, and then we'll get started. So we're going to cover, this is going to be a two-part lecture. This is going to be, part one will be 7.3, and part two will be 7.4. The goals are pretty straightforward. We want to understand and successfully use sets. And the reason for using sets is going into probability. Sets are a basic to understanding how to work with probability. So today, in this part, we're going to just do this first part here, which is understand and successfully count using sets. Successfully count. So most people, if you ask them, they'll say, "Yeah, I know how to count. Thank you. I'm pretty good at that." And while this is in fact true, the foundation of counting actually begins in sets. And gaining a strong understanding of how to count using sets will go a long way to working with probabilities in the next chapter. So, what you're used to, how we typically count, is if a college chemistry class consists of 13 males and 15 females, then a total of 28 students are enrolled in the class. If we're going to write this in terms of sets, we're going to say something along the lines of, if M is a set of male students in the chemistry class and F is a set of female students in the class, the union of the sets M and F, denoted by M union F, is the set of all students in the class, which is equal to 28. These sets have no elements in common, therefore the intersection M intersect F is the empty set, and M and F are disjoint. The number of elements is denoted by N M union F and is given by M union F is equal to the number in M plus the number in F, which again equals 28. Okay, that seems like an awful lot of extra work. And for a simple problem like this, it is in fact. But when you get into more complex problems where it's not always easy to see the difference between the sets and where you have a lot of interactions going on, it sure does make it a lot easier to have a good, strong understanding of sets. And when we're doing probability, this is in fact the case. Now, when counting, what we just gave is not always the case. For example, a math class might have 22 math majors, 16 physics majors, and 7 students who are in both math and physics. So how do we frame that? So then we would say the number of male students, math majors intersect union, excuse me, the number of math majors and the number of physics majors is equal to the number of math majors plus the number of physics majors minus the number who are both, which in this case is 22 plus 16 minus 7, which equals 31. So this kind of gives us a basic principle for counting in any two sets. And that is the number of elements in the union of two sets. The number of elements in the union is equal to the number of elements in A plus the number of elements in B minus the number of elements in their intersection. Why? Let's see if we can clarify this. So if we're generally writing it, so let's say we have set A and set B. We want to make a union of them. It's just plus. So if this is 7 and this is 5, our union is 12. That seems pretty clear. I think that's pretty easy. Let's try it again. Now, let's say we have, and this time I'm going to intersect them. Let's put 7, 6, and 3. So this is A, and this is B, A has 13, B has 10. What we're doing is counting 7 twice. So we're counting it when we're counting it in part of A, and we're counting it when we're counting it in part of B. So in order to get the correct answer here, we must subtract off 7, which is the intersection. Now let's work out an example. According to a survey of business firms in a certain city, 345 firms offer their employees group life insurance. We're going to call that GL. 285 offer long-term disability insurance, which we're going to term D. And 115 offer group life and long-term disability insurance. And that is, they offer both. So it's and, that's an intersection. How many firms offer their employees group life insurance or long-term disability insurance? That's a union. Well, let's think about it just a little bit. The way we've been phrasing this, how many offer group life or? So that's a union. So that is N, group life, union, disability. And we refer back to the addition principle, which is just above us, and that equals the number in GL plus the number in D minus their intersection. Which is exactly what we're showing here. So if we do that, we end up with 515. So now that you've learned how to count, let's learn how to multiply. So if two operations, let's call them 0, 1 and 0, 2, or operation 1 and operation 2, are performed in order, so you do operation 1 first, and then you do operation 2, with n1 possible outcomes for the first operation, and then 2 possible outcomes for the second operation, then there are, in total, n1 times n2 total operations available to you. Okay? So if I were to say there were 5 ways that you could walk to school, and then once you're at school, there are 3 ways you could walk to the cafeteria. That would tell you that in total, there are 5 times 3 ways you can walk from your starting point through school to the cafeteria. So that would be 15 total different ways you could do that. That is the possible combined outcomes of the first operation followed by the second operation. And you can just keep adding these on. So basically multiply, 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 multiply. So in general, if n operations, 0, 1, 0, 2, up to 0n, order n, are performed in order with possible outcomes n1, n2, up to nn, respectively, then there are n1 times n2 times ... end of the n operations available. Possible outcomes of the operations performed in that particular order. If you change the order, you might very well change the result. And we'll see some examples of how that works in just a moment. So, code words. How many 4-letter code words are possible using the first 10 letters of the alphabet? Okay. First 10 letters of the alphabet. No letter can be repeated. So once you use a letter, you take it out. So that means for the first operation, so there's 10 possibilities. And then you remove that as a possibility, which means that for the next time, there's 9 possibilities, then 8 possibilities, and then 7 possibilities, which gives us a total of 10 times 9 times 8 times 7. So there's 5,040 ways. So there's 5,040 four-letter code words that are possible using the first 10 letters of the alphabet if no letter is repeated. Now we're saying letters may be repeated. That means that there's 10 possibilities for the first letter. There's also 10 possibilities for the second letter. And there's still 10 possibilities for the third letter. And 10 possibilities for the fourth letter. So that'll be 10 times 10 times 10 times 10, which is 10,000 ways. It's quite a bit more possible ways, possible four-letter code words. Now let's think of this. Adjacent letters must be different. That means you can't have an A next to an A or a B next to a B. So let's try this. Let's try this without looking ahead. So order 1, I'm going to write it, is still going to be 10. The second one, it can't, so whatever letter you picked and you put in this first spot, you can't pick it again. So it's 9. Again, whatever letter you have in this spot, you can't pick it again. But the previous one you can. So it's still 9. And then the last one is also 9. So it's 10 times 9 times 9 times 9. Which in this case is 7,290 different four-letter code words. And that is where we're going to end in this part. The next part is permutations and combinations. I think the easy way is to just practice along with these a little bit. I don't necessarily know that I need to do more examples of these. If you, like I say, practice. And we'll see a lot more of this when we're doing permutations and combinations. Thank you.